Good evening, everyone. In the last lecture, we discussed about the current electricity. We discussed about the charge and the current, flow of current, and what was the source of flow of current. It was the source potential difference, and because of the potential difference, the current is set up within the conductor, and the current is defined as the uh, rate of flow of charge with respect to time, right, through the area of cross section of a conductor, right? But today we'll be discussing about we'll try to derive the microscopic form of Ohm's law. And before discussing the microscopic form of Ohm's law, we'll be discussing about the mean free path, right? So the you know that inside a conductor, let's suppose this is the conductor, right? Let's suppose this is a conductor, right? If this is the conductor and inside the conductor, what happens is that the charges or the electrons flow, right? And these electrons, while moving inside a conductor, continuously collide with the atoms of a conductor, right? Continuously collide with the atoms of a conductor, right? And it means that there are successive collisions. You can see in this picture, right? This is the internal structure of a conductor, right? What happens is that this is the atom, these are the atoms in a conductor, and this is the electron, right? When we apply the battery or the source of potential difference, when we apply the source of potential difference to the conductor, the electric field is set up, and because of that electric field, the electrostatic force acts on the charge, and the charge starts to move, right? You can see that here, because of the electric field, this electron starts to move, right, in this direction, right? And after some time, this uh, electron strikes this atom and is collides with atom and is reflected back, and again this electron is going to strike this atom, and so on and so forth. This process will be repeated again and again, right? So this is how the collision of electrons occur with respect to the or with the atoms of a conductor, right? So you can see that here, so you can see that for the first collision, right? For the first collision here, the electron travels a distance of lambda 1, and for the second collision, it travels a distance of lambda 2. And the time taken for the first collision to occur is tau 1, and the time taken for the second collision to occur is tau 2, right? You can see that for each and every collision, the distance traveled by the electron for each and every successive collision is different, and the time taken by the electron for each and every successive collision is also different, right? So it means that we can define the average distance, right? Because the distance for each and every collision is different, right? It cannot be same, it will be different. So what we can do is that we can define an average distance traveled by the particle, right? Or we can define by the average distance traveled by the free electron between two successive collisions, right? So this average distance traveled by this electron during the successive collisions between two successive collisions, that's what we call as mean free path. So mean free path is nothing. It's the average distance traveled by the electron between two successive collisions, right? So that's what we call as mean free path. And the average time taken by this electron between two successive collisions, right? We call this as relaxation time, right? We call this as relaxation time. So this is the mean free path is nothing. It's the average time, right? It means that lambda is the mean free path, right? It's nothing. If the lambda 1, lambda 2, and lambda 3, and so on, these are the distance traveled by this electron in n collisions, then the mean free path will be lambda 1 plus lambda 2 plus lambda 3 up to so on, divided by the n. So this lambda is going to be the mean free path, right? Mean free path. So this is nothing. Mean free path is the average distance traveled by this electron inside the conductor between two successive collisions, right? So similarly, we define the relaxation time, and the relation with electric current relaxation time also will be defined. Like you can see here, there is a time taken by this electron between two successive collisions, and this time is different for two different successive collisions, right? For two different collisions, it means that the time taken by this here for the first collision is tau 1, and for the second collision is tau 2. It means that for each and every successive collisions, the time taken by this electron will be different, right? That's why we define an average time, or we can say mean relaxation time. This is nothing. This is the time taken by free electron between two successive collisions to occur. That's what we call as relaxation time, right? So it means that if between n collisions, tau 1 plus tau 2 plus tau 3 up to so on, these are the times taken by the electron between two successive collisions, then the average of these times will be nothing. That's what we call as That's what we call as mean relaxation time, right? This is nothing. This is mean relaxation time. We can call it as mean relaxation time, right? It's denoted by tau, right? Tau is nothing, it's the relaxation time, right? So where two quantities here, one is the mean free path, is the average distance between two successive collisions inside the conductor covered by the electron, and similarly, mean relaxation time is the average time taken by the electron between the two successive collisions inside the conductor, right? And now let's move on to the concept of the drift velocity and mobility, right? Drift velocity and the mobility, right? So you can see that here electron we are applying a battery here. Battery is a source of potential difference, right? If the battery is a source of potential difference, and what happens is that this battery is a source of potential difference, and this battery provides an electric field E, right? This electric field E is nothing. Let's suppose this is the length of this conductor L, and battery is a source of potential difference. V be the potential difference. Then electric field is nothing. It's V upon L. This will be the electric field across the ends of this conductor, right? If this is the electric field across the ends of the conductor, right? E is the electric field across the ends of the conductor. Then the force acting on the electron will be nothing. It will be equal to force will be equal to minus E, because it will be opposite to the electric field, right? Minus E, right? E is the charge of electron, right? E is the charge of electron. That's 1.6 into 10 to the power minus 19 coulombs, right? This will be the charge of electron, and E is the electric field, right? And if we calculate the acceleration of this electron, that will be nothing. It will be equal to force upon the mass of electron, right? Force upon the mass of electron. That will be minus E multiplied with the electric field E upon the n, right? This will be the magnitude of the acceleration of the electron, right? So it means that if we have n number of electrons, right? If we have n number of electrons, let's suppose we have n number of electrons, right? Suppose this is the electron 1, it's having an initial speed as u1, right? u1, correct? And it travels for it is having an acceleration a, and it travels for a time tau 1, right? And similarly, we can have its final velocity as p is equal to or we can write v1 is equal to u1 plus a tau 1, right? A tau 1. So this will be the final velocity after some time tau for this electron. Similarly for second electron, right? For second electron, we will have the final velocity as v2, right? And let's suppose its initial velocity was u2, and its acceleration is again a. That's let's call this time for this electron as tau 2, right? So tau 2 is electron time for this electron, right? This will be the final velocity. Similarly, for another electron, we will have v3 as v3 will be equal to u3 plus a tau 3, right? Right. So this is the final velocity of the electron, right? For n number of electrons. Similarly, for nth electron, right? For nth electron, we will have velocity as Vn, that will be equal to Un, right? Plus a tau n, right? Correct? So drift velocity is nothing. We can see that each and every electron is having different time between two successive collisions, right? And it will have different initial velocities or different initial speeds. We can see that the final velocities are also different for different final velocities are also different for different electrons, right? So we'll be defining the average speed for these electrons, right? With which they are moving, right? So if we try to find this average speed is nothing. This average speed for these electrons we call as drift velocities, right? That's what we call as drift velocity, right? So we'll be doing nothing. It will be v1 plus v2 plus v3 plus so on up to vn and divided by n, right? Divided by n, correct? So this will be the average velocity for these electrons, right? That average velocity, what we call as drift velocity, it means on an average, these electrons will be drifting inside the conductor with this velocity, what we call as drift velocity, right? Vd, represented by Vd. So it means that if we substitute the value of V1, that will be U1 plus A tau 1 plus so on, U2 plus A tau 2, right? Plus so on up to un plus a tau n, right, upon the n, right, upon n. We can just rewrite it as u1 plus u2 plus so on up to un divided by n, right, and plus a times a will be common, right, tau 1 plus sorry, it's not a vector, tau 2 plus tau 2 tau 3 up to so on up to tau n, right, divided by the vector n, right. And you can see that this is nothing, this is the average initial velocity, right? And we know that electron initially was moving in the random direction, right? Random direction, right? And the average initial velocity, u average initial velocity will be equal to 0 because the electron is moving in the random directions. The total average will be always equal to 0, right? So this u1 plus u2 plus un upon n has to be equal to 0 for this electron, right? So we can write it as Vd equal to as a, what is this tau 1 plus tau 2 plus tau 3, right? We just discussed it. It is nothing, is the relaxation time, right? It's the mean relaxation time. We can write it as a tau, right? So this is the mean relaxation time. So it means that a is nothing. A is given as ee upon m. So we can write it as ee tau upon m. So right. So it means our drift velocity is nothing. That's equal to charge of electron multiplied by the electric field tau upon m. That's the drift velocity, right? This is the drift velocity. So this is the drift velocity, right? So drift velocity of electron is nothing. It's given by E tau upon m, where tau is nothing. It's the relaxation time or mean relaxation time. And m here is the mass of electron, E is the electric field, and E is the charge of, small e is the charge of electron, right? So this is the relation between drift velocity and electric field, right? Then there is another term we call as mobility. Mobility is nothing, it's the drift velocity per unit electric field, right? Mobility is defined as drift velocity per unit electric field. That's Vd upon E, right? Vd upon E will be the drift velocity, right? So sorry, mobility, right? So we can write this mobility as E tau upon m, right? So our drift velocity is E tau upon m divided by the electric field E. So this will get cancelled. So we'll be left with the mobility as, mobility will be nothing. It will be charge of electron multiplied by the relaxation time upon the m. So this is what we call as mobility, right? So this is the mobility of the electron. So mobility is defined as the drift velocity per unit electric field, right? So let's move on to the next concept. The concept is the relation between drift velocity and the current, right? Where to find the relation between the drift velocity and the current, right? Let's suppose that let's suppose n is the number density of a conductor, right? Let's suppose that n is the number density for the conductor. N is the number density. N is the number density of a conductor. Is the number density of a conductor. By number density of a conductor, we mean to say that it's the number of electrons per unit volume. Is the number density of conductor. So number density is nothing. Number density is nothing. N is nothing. It's the number of electrons per unit volume, right? Number of electrons per unit volume of a conductor, right? Volume, right? Let's suppose we are taking this conductor here, right? This is the conductor here, right? And area of cross section of this conductor is A, and length of this conductor is L, right? Right? Length of this conductor is L, right? Then let's suppose n is the number density of this electron, right? If n is the number density, then number of electrons in this volume will be number of electrons in this volume will be nothing. It will be equal to the number density multiplied by the volume of this conductor. So number density is n, and the volume of this conductor is number of electrons in length L. We can write in length L will be equal to number density, that's n, and the volume of this conductor, that's A multiplied by L. So the number of electrons will be nothing, n A into L, right? So this is the number density of this what we call as number of electrons present in this volume of this conductor, right? Now the question is that we have to establish a relation between drift velocity and the current, right? We know that current is nothing. It's defined as the delta Q upon delta T, right? Delta Q upon the delta T. So delta Q upon delta T will be the current, right? If delta Q upon delta T is the current, then we have to find the charge, right? Then delta Q charge is nothing. Delta Q charge will be the total number of electrons multiplied by the charge of electron, right? So delta Q will be equal to N multiplied by the charge of electron A into L, right? N multiplied by the charge of electron A into L. So this will be the what we call as the charge, right? Charge flow. And we know that drift velocity is nothing. It's E tau upon m, right? Tau upon m, right? So E tau upon m is the what we call as the drift velocity, right? So we can see that drift velocity is equal to E tau upon m, right? Or here, we can write here E is also equal to V upon L, right? V upon L. E is equal to V upon L. So this is our equation. Let me call this equation first and this is the equation second, right? Equation first and equation second. So drift velocity is charge multiplied by the electric field multiplied with the relaxation time tau upon the m. Now we have to calculate this current delta Q upon delta T. We can see that this current will be nothing. It will be equal to V D A N E, right? V D A N E. V D is nothing. It's the drift velocity, right? Drift velocity, right? And A is the area of cross section. A is area of cross section. Area of cross section, and N is nothing. It's the number density. Number density. If N is the number density, E is the charge of electron, right? Charge of electron. E is the charge of electron, right? So this is how we how we find the current because of relation between the current and the drift velocity. So current is nothing. It's the drift velocity. It's nothing. It's drift velocity times area into number density multiplied by the charge of electron. So we can write this relation here. The current is nothing. It's V T A N E, right? E is the charge of electron, right? E is the charge of electron, right? So it means that the current is directly proportional to the drift velocity. Greater the drift velocity of electrons in a conductor, greater will be the current flowing through it, right? So that's how we find the relation between the drift velocity and the current, right? Now, another important concept related to the current is the current density. The current density is defined as the current flowing per unit cross-sectional area of a conductor, right? It's defined as the current flowing per unit cross-section area of a conductor, right? So you can see here that these are the two conductors, right? This is the conductor one here. This is the conductor one. This is the conductor two here, right? You can see through this conductor, this is the direction of the current, right? In this direction, the current is flowing, right? And this is the area of cross section, right? The current is flowing perpendicular to this cross sectional area, right? Now, this current density will be defined as the current flowing through this perpendicular cross sectional area. That's what we call as current density, right? So current density is actually a vector quantity. It's a vector, right? It's a vector. It's a vector quantity, and this vector gives actually us information about the direction of the flow of current, right? This gives us the information about the direction of flow of the current, right? So current density is a vector quantity, right? Having direction of electric field or direction of current flow, right? So one more important point is that let's suppose this is the area of cross section, right? And this is the current flowing. Then the direction of this area of cross section is along this direction, right? But we have to find the current density. Current density is the current perpendicular to the area, right? So we'll just take area component of area like this. So it will be a cos theta, right? And this a cos theta component of this area will be perpendicular to this current I. So here in this case, the current density will be nothing. It will be I upon the perpendicular area, that is A cos theta, right? So this will be the current density, right? And one more important point is that surface area is normal to the to the direction of charge flow, right? Surface area is always normal to the direction of the charge flow. So that's these are some of the important points about the current density. So current density, it's a vector quantity. It tells us about the direction of the current flow, right? Whatever the direction of the current density, same will be the direction of the flow of current, right? Same will be the direction of the flow of current, right? So we'll be discussing about the microscopic form of Ohm's law, right? Before discussing about the microscopic form of Ohm's law, right? Before discussing the microscopic form of Ohm's law, we'll just discuss about the Ohm's law. Then we'll be discussing about the microscopic form of Ohm's law as well, right? So here in this case, we just if we try to develop the relation between the electric field and the current density, right? We see that here our current density is given as J is equal to I upon A, right? If the current density is J is equal to I upon A, it means it's the current upon the A, right? And we have developed a relation between the current and the drift velocity, right? You can see that this current I is nothing, it's equal to VdA right? VdA right? We can write it here, drift velocity A times NE, right? Upon A, right? You can just cancel A with A here, will be left with drift velocity, right? N into E, right? Drift velocity N into E, where N is the number density, right? It means that we can write this J current density as V is the drift velocity. We can just write it as Vd here, right? Vd multiplied by Ne. And we know that this drift velocity we just calculated in the last slide as it was charge of electron E tau upon m, right? We can write it as E tau upon m. So it is E tau upon m, right? Multiplied by the n into E, right? So we can rewrite it as Ne square tau upon m multiplied by E, right? Or we can write it as J is equal to let's replace this Ne square tau upon m with the factor sigma and E, right? Factor sigma and E, right? So it means that our Ne square tau upon m, we call this as sigma, right? Sigma, it's nothing, it's what we call as conductivity, right? Conductivity. So this is nothing, this is the conductivity, and you can say that this conductivity of the conductor depends upon the average relaxation time. It depends upon the mean relaxation time. So sigma is directly proportional to tau, that's mean relaxation time, right? Mean relaxation time. So sigma is directly proportional to the tau, that's mean relaxation time, and we call this sigma as conductivity. It means that conductivity decides which material is a better conductor of electricity and which material is not a better conductor of electricity. That's the significance of what we call as sigma, conductivity, right? So conductivity gives us the information of which material is a better conductor and which material is a poor conductor of electricity. And this J is equal to sigma E. J is equal to sigma E, right? This J equal to sigma E is what we call as J is equal to sigma E, right? This equation we call as microscopic form of Ohm's law, right? This is nothing. This is what we call as microscopic form of Ohm's law, right? Microscopic form of Ohm's law. So this is nothing what we call as microscopic form of Ohm's law, right? So J is equal to sigma is the microscopic form of Ohm's law, right? It shows that the direction of the current density is along the direction of the electric field vector, right? So this is what we call as microscopic form of Ohm's law, right? Now let's discuss about the Ohm's law, right? Experiment in particular, right? And let's discuss about the VI characteristics as well, right? We'll be discussing about the Ohm's law and the VI characteristics of Ohm's law as well, right? So you can see here in this picture, uh, what Ohm's law states that the potential difference or the current flowing through the conductor, right? If we have a conductor like this, right? This is the conductor, and we are placing a source of potential difference, that's the battery, across the ends of the conductor, and the current, if the current I is flowing through the conductor, right? If I is the current flowing through the conductor, then this potential difference across this conductor will be directly proportional to the I current I flowing through this current conductor, right? So it means that V is directly proportional to the I. It means that greater the potential difference across the ends of the conductor, greater will be the current flowing through the conductor, right? So it means that potential difference across the ends of a conductor is proportional to the current, right? And this observation was done by Ohm at same temperature, right? Provided it's at same temperature. It means that if the temperature of a conductor is same, then potential difference across the ends of a conductor is directly proportional to the current flowing through the conductor, right? What he observed that he actually plotted the current versus potential difference graph. That's he plotted IV characteristics, right? At different potential differences and measured current at different potentials, right? And he found that the equation or the graph between the current and the potential difference was found to be a straight line, right? It was found to be a straight line. And from this, if it is a straight line, we can clearly see that then potential difference is proportional to the current, right? If it is a straight line graph, right? So this was the observation done by Ohm, right? He did this observation that at different potential difference, the current flowing through the conductor changes, right? And it's directly proportional to the potential difference. If we increase the potential difference, the current through the conductor is going to increase, right? But at the same temperature. He did not change the temperature. If the temperature changed, then the things are different altogether, right? But at the same temperature, V is proportional to I, right? V is proportional to I. So at the same temperature, the V is proportional to I, or we can say that V by I ratio, it's a constant, right? We can just replace the proportionality with some constant, right? And this constant V by I is a constant, and he observed that the ratio V by I is a constant, and this constant is nothing. This constant is nothing. Is it's a slope of this constant is nothing. Slope of VI characteristics or VI graph, right? VI graph. So this constant was nothing. It was a slope of VI graph, right? Slope of VI graph. And later on, it was said that this constant is nothing. This is what we call as the resistance of a conductor, right? R. This is nothing but the resistance of a conductor, right? This is nothing but resistance of a conductor. This is nothing but a resistance of a conductor, right? So R is the resistance of a conductor, right? So Ohm's law is nothing. It's V by R is constant. V by I is constant, right? That's equal to R. This is what we call as this statement, or this equation is what we call as Ohm's law, right? This equation we call as Ohm's law, right? And previously we discussed about the microscopic form of Ohm's law, right? As well, right? So this R is nothing, it's a resistance. It means that resistance of a conductor is constant at constant temperature. If the temperature does not change, the resistance of a conductor remains same, right? Otherwise, resistance do depend upon the temperature of a conductor. At different temperatures, the resistance of a conductor is different. It's not same. So we'll see later on how the resistance of a conductor change with the change in how the resistance of a conductor change with the change in what we call as temperature, right? So you can see two graphs here. One first graph is IV characteristic. It's also a straight line, and VI characteristics. It's also a straight line, right? So it means that the slope will be constant for both the cases. It will be a straight line for the both the cases. If we plot IV characteristics or VI characteristics, slope will be a constant. Or we can say that slope here is nothing. Slope is nothing. It's the tan of theta, right? Tan of theta, right? Tan of theta is the slope here, right? Tan of theta, right? So tan of a slope of IV characteristics, if we plot I on the y-axis, right? For this case, if we plot I on the y-axis and V on the x-axis, then the slope is nothing. Slope will give us 1 upon R, right? That's equal to tan of theta, right? And similarly for VI characteristics, the slope is nothing. That's tan of theta. That's equal to slope once again, but that will be equal to V upon I. That's equal to R, right? So slope of IV characteristics will give us the reciprocal of the resistance, and the slope of VI characteristics will give us the resistance, right? So that's the conclusion from the two characteristics here, right? Let's move on. Let's discuss about the IV curve here, right? There's a question here. We can see there are two IV characteristics, right? There are two IV characteristics here. This is graph 1 and this is the graph second. Here you can see that in both the graphs the two characteristics are different, right? And we have to see which resistance is more and which resistance is less. So definitely it's going to be for two different conductors, or we can say that these are the resistance at two different temperatures as well, right? So this is conductor 1, conductor 1, conductor 1, and this is conductor 2, right? Conductor 2, and we know that slope is nothing. Slope is for slope of IV plot gives us 1 upon R, right? Correct, 1 upon R, and the slope is nothing, is the tan of theta. For the first graph we can see the slope is nothing, is the tan of 60 degree, right? Tan of 60 degree, that's equal to root 3, right? And for the second plot the slope is tan of 30 degree, that's equal to 1 over root 3, right? 1 over root 3, right? Let me call this as 1 over R1, right? And let me call this as 1 over R2, right? So this is our first equation and this is our second equation, right? We can just divide these two to calculate the ratio between first and two. That's 1 upon R1 upon 1 upon R2, right? That will be equal to root 3 over 1 over root 3, right? So it will be equal to root 3 square. That's equal to 3, right? Correct. So it will be nothing, it will be R2 upon R1, right? That's equal to 3, which implies that R1 over R2 will be equal to 1 by 3, right? R1 over R2 will be equal to 1 by 3. It means that R1 is having less resistance as compared to R2, right? So R1 is one third of R2, right? R1 is one third of R2. So this is how we can calculate the resistance of a conductor using the IV characteristics. So slope of the IV characteristics gives us information about the resistance of a conductor, right? Which is constant at constant temperature. Otherwise, the resistance is going to change. The resistance is different at different temperatures, right? So the resistance is different at different temperatures. Let's move on to the next concept here. Now in this case what we can do is that we can just establish Ohm's law from the we can establish Ohm's law from the microscopic form of Ohm's law, right? Let's suppose that we have this conductor here, right? This is the conductor here, this is the conductor here, right? This is the conductor, this is the conductor here, and this conductor has been supplied with a potential difference of V, right? This conductor has been supplied with a potential difference of V across its ends, right? If V is the potential difference across its ends and L is the length of this conductor, right? And A is the area of cross section of this conductor, right? A is the area of cross section of this conductor. So we can see that our microscopic form of Ohm's law is nothing that J is equal to sigma E, right? Sigma E, and J is nothing. J is our current density. That's I over A, right? I over A. We can just write, we can replace J with I over A, right? I over A, that's equal to sigma E, right? Sigma E. And we know that electric field has been set up. This is the electric field, right? E inside the conductor, and this electric field E is nothing. It's equal to potential difference across the ends of the conductor divided by the length of this conductor, right? So this is the electric field, right? So it means that we can just replace E with V over L, right? V over L. If we replace E with V over L, so it means that our I over A will be nothing. That will be equal to sigma V over L, right? Sigma V over L, correct? Sigma V over L. So let's calculate the ratio V over L here. V over L, V over I will be nothing. It will be equal to V over I will be equal to, so this is our sigma V over L, right? So we have to calculate V over I. So it will be equal to L upon sigma A, right? L upon sigma A, right? L upon sigma A. And sigma is nothing. It's the sigma, what we call as sigma is sometimes 1 upon sigma. We call it as rho, right? This is nothing. This is what we call as resistivity, right? Resistivity of a conductor, right? Sigma rho is nothing, is the resistivity of a conductor, right? Resistivity of a conductor, right? Resistivity of a conductor, right? And if we replace 1 upon sigma with rho, so we will get V upon I equal to rho L upon A, right? And we know that this rho L upon A is nothing. This is that resistance of a conductor, right? Resistance of a conductor. Resistance of a conductor. Right, we can see V over I is constant, that's equal to R. So rho L upon A is a constant, that's equal to R. That's nothing but resistance of a conductor. So the resistance of a conductor depends upon the two factors, right? One factor is the length of the conductor, another is the area of cross section of a conductor, right? So there are two factors on which the resistance of a conductor depend. One factor is the length of a conductor, another factor is the area of cross section of a conductor, right? So let's discuss about the resistance of a conductor, right, in some details, right? So the resistance is nothing. Resistance. So resistance of a conductor, can discuss it, and the factors affecting the resistance, right? So it means that from the discussion in the last slide, let's suppose we have this conductor here, right? If the length of this conductor is equal to L, right? And the area of cross section of this conductor is equal to A. A is the area of cross section for this conductor, right? A is the area of cross section, right? It means that the resistance of this conductor will be directly proportional to the length of this conductor, and resistance of this conductor will be inversely proportional to the area of cross section for this conductor. Let me call this first and this is second. It means that we can write it as R is directly proportional to L over A, or replacing proportionality with a constant, and that constant what we call as rho. That's rho L upon A, right? And this rho is nothing. This is what we call as resistivity, right? This is what we call as resistivity. So resistance of a conductor depends upon the length of the conductor. It means the greater the length of a conductor, greater will be its resistance, right? And lesser the area of cross section of the conductor, greater will be its resistance, or greater the area of cross section of a conductor, less will be its resistance, right? So resistance of a conductor depends upon mainly two factors: length of the conductor and area of cross section, right? Now this quantity, that's what we call as the resistivity. Let's suppose if we take length of a conductor L as 1 unit, right? 1 unit, 1 unit, and area of cross section as 1 unit square, right? 1 unit square. Then this rho will be nothing. This will be equal to R, right? So we can say it's a resistance of a conductor of 1 unit length and area of cross section as 1 unit square, right? Resistance resistance of a conductor resistance of a conductor of 1 unit length and area equal to 1 unit square, right? Area equal to 1 unit square, right? So that's the resistivity of a conductor, correct? So this is how we define the resistivity of a conductor, right? Now this resistivity depends upon uh, only two things, right? This resistivity depends upon two things. It depends upon the nature of material, right? Nature of material, right? And it also depends upon the temperature, right? Temperature. So there are two factors on which the resistivity of a material, resistivity of a conductor depends. One factor is it depends upon the nature of material, right? It depends upon the nature of material. Second factor is depends upon the temperature. So it means that resistivity resistance also depends upon the resistance also depends on nature of material, right? Because for different material the resistivity will be different, and for different temperature resistivity will be different. So resistance also depends on nature of material and temperature, right? Nature of material and temperature. So these are the important factors on which resistance of a conductor depends. Now, first factor is the length of a conductor, another factor is the area of cross section of a conductor, and the third factor is the nature of material of a conductor, and the fourth factor is external temperature. So on the external temperature as well, the resistance of a conductor increases, and we can see that resistance of a conductor increases on increasing the temperature. So if the temperature of a conductor is increased, right? If we increase the temperature of a conductor, then the resistance of a conductor increases. And if we decrease the temperature of a conductor, the resistance of a conductor decreases. So we'll be discussing in detail the temperature dependence of a resistance of a conductor in the next lecture, right? So till now we discussed about microscopic form of Ohm's law. We discussed about the Ohm's law, right? That's V upon I is equal to constant. And we discussed about the factors on which the resistance of a conductor depends. And in the next lecture, we'll be discussing some of the problems or the questions related to all the content that we discussed till now. And we'll be also discussing about the factors affecting the resistance. That's the temperature dependence of a resistance. How actually the resistance depends upon the temperature. So that will be discussed in the next lecture, right? So till then, take care and goodbye.